Good afternoon, Semester 2, Geometry Semester 2 class. And here's the pretest analysis for Unit 3. So question number 1, so which of the following best describe the basic postulate of Euclidean geometry? So we do know that a circle measures 360 degrees, and all isosceles right triangles are similar, or lines continue indefinitely. So the thing is that the one that can be considered the Euclidean geometry. So for the basic postulate, we'd be saying that a circle can be drawn with any center and a radius. Okay, so a circle can be drawn with any center and radius. So this one is the most correct one. And then for the next one, which of the following best describe a basic postulates of Euclidean geometry? Any straight line segment can be extended indefinitely. Okay, so that's another one. And 1C, which one of the following best describe the basic postulates of Euclidean geometry? A straight line segment can be drawn between any 2 points. Okay, so that's another one. And question number 2. So which of the following polygon can be constructed using 6 equilateral triangles? So 6 equilateral triangles, so if you just try to form all of them together, then that would be considered a hexagon. So the prefix of hexa, so that means 6. So 6 equilateral triangles. And which of the following is needed to construct the figure below? So this one's a hexagon, so 6 equilateral triangles. So you put a center here, and then you just divide it into 6 congruent equilateral triangles. And which of the following is needed to construct a hexagon? So that would be 6 equilateral triangles, a similar questions. And which of the following is the measure of angle AXY if ray XY bisects angle AXB? So which measures 110 degree? So half of 110 bisect, that means you want to take half of it. So half of 110, then that'll be 55 degrees. So here's another one. So take half of 70, then you get 35. And then half of 86, then you get 43. And which type of angle is formed by the intersection of the perpendicular line segment below? So this one, obviously, it's a right angle. Can it be acute? Can it be obtuse? Can it be straight? But you see the right angle here. So it's a right angle. So the measure of the right angle is always 90 degrees. And then question number 5. So which paper folding method can be used to form the midpoint of a line of symmetry, a line segment? So you begin with the line segments on the paper and fold the paper so that the segments endpoint line on top of each other. So that it's doing for some kind of origami. So let's say that I want to make the line segments of the midpoint. So you follow through the first process here. And which of the following can be constructed by drawing a line segment on paper, then fold the paper so that the endpoints of the line segment, the segments line on top of each other, midpoint of a segment. Again, this one is all about the midpoints for folding the line segment. And which paper folding method can be used to form a perpendicular line segment? So you begin with a segment and a point not on the segments. Fold the paper through the point so that the given line segment line upon itself. Okay. And which of the following can be constructed by the folding method? So begin a segment and a point not on the segment. So this one is just like a converse statement of the previous one. So that's a perpendicular line segment. So which is quite similar. So 6C is also like that. So which of the following best describe the folding method need to create the perpendicular line segments? So fold tracing paper at a point not on the line segment so that the line segment lies upon itself. And question number 7. Which paper folding method can be used to form an angle bisector? So begin with an angle on the tracing paper and then fold the paper so that the ray forming the angle lie upon each other. Okay, so it's all about the angle bisector, the folding paper method. And then question number 8. So which of the following can be constructed using folding method below? Begin with the segment and the point not on the segment. Fold the paper at the point so that the line segment line area upon itself. Unfold the paper, then fold it again at the point so that the fold just make lines evenly upon itself. So this one is about making the parallel lines. Again, the way to make the parallel lines. And which of the following is construction so that was never accomplished, but agreed using only a compass and a straight edge. So just use a compass and a straight edge. You can make an angle bisector. You can doubling a square. You can trisect a line segment, but you can never trisect any given angle. And which of the following is construction that was never accomplished by the Greek, using only a compass and a straight edge? And also doubling a cube. Okay, so doubling a cube can be doubling a square, but it cannot be doubling a cube. And which of the following were the two types of construction that were never accomplished by the Greek using only compass and a straight edge? Trisecting any given angle and a doubling a cube. So that's something, the Greek cannot do before. And which of the following angle can be trisect using only a compass and a straight edge? So let's say that you form a 90-degree angle. And which of the following angle can be trisect using only a compass and a straight edge? 45 degree. Well, I'll try to trisect that. It's considered what, 15? Each angle would be considered 15 degree. So the next one, which of the following group of angle can be trisect using only a compass and a straight edge? All right angles. So you divide it 90 degrees, then that'll be 30, 30, and 30. And which of the following most famous impossible problem from Greek antiquity? The Dalian problem. And which of the following associate with the famous impossible Dalian problem? So you try to double a cube, so then that's impossible. So mainly this whole chapter or the unit, it's all about the transformation. So the rest of the problem here, it's all about transformation. So which one of the following does not describe a rigid motion transformation? Enlargement, so anything that's enlargement, like making it bigger or shrinking, it's not considered the rigid motion. The rigid motion guarantee that it doesn't matter what kind of transformation that you do. The original shape, it's going to be the exact same size as the one after you transform. But the enlargements, enlarging a figure by scale factor of 2. So this one is not considered part of the rigid motion transformation. And for the next one, which of the following does not describe a rigid motion transformation? Dilating a figure by scale factor of 1/4. Again, anything that's considered enlargement, shrinking, dilations, you all consider, it's not considered part of the rigid motion transformation. And also the next one is quite similar. And for the next one here, which of the following steps would apply to ABCD to obtain A prime, B prime, C prime, and D prime? So here's ABCD, and then we want to transform the figure to A prime, B prime, C prime, and D prime. So this one is shift 3 units to the right and then 2 units down. So from this figure to this figure. So count it from point B to B prime. So it's 3 units to the right, and then 2 units down. Count it, 3 to the right, 2 units down. And then the next one is quite similar. So this one started with the trapezoid A, B, C, D. And then you want to transform that to A prime, B prime, C prime, and D prime. So shift 2 units to the right, and then 3 units down. So from B to B prime, or from A to A prime, 2 units to the right, 3 units down. And the other figure here, so it's quite similar. So you just need to count it from one point to another point. Okay, so from A to A prime, B to B prime, and then C to C prime. So I just enlarged the figure a little bit. So A to A prime, B to B prime, C to C prime, D to D prime. So you just want to count a unit. So 3 units to the right, 4 units up. And which of the following transformation will result in an image that maps onto itself? So anything that you consider reflecting across the x-axis, and then you reflect it again across the x-axis. So that means it's going back to the exact same position. And the other one is quite similar, reflecting back and forth on the y-axis. And then for C, across the line, and then reflect across the same line again. So it's getting back to the original position. And what transformation would apply to ABC to obtain A prime, B prime, and C prime? So ABC to A prime, B prime, C prime. So this one looks like has something to do with the rotations and then the reflections. So rotate 90 degrees counterclockwise and then shift 2 units up. So this one has something to do with the rotation and then the translations. So anything that's considered rotating, then that'll be rotation. Shifting, moving up and down, left to right, so that would be considered translation. And then here's another one, triangle ABC to obtain A prime, B prime, C prime. So here's ABC. So in order to get A prime, B prime, C prime, so first thing is about rotations. 180 degree, counterclockwise, going back this way. And then shift 2 units down. And what transformation will apply to ABC to obtain triangle A prime, B prime, C prime? So again, so here's the triangles, the original one, and then after the transformation, so here's what we got for A prime, B prime, C prime. Again, this one has something to do with the rotation and also the translation. So it rotates 270 degree counterclockwise, and then shift 3 units up. And the other one, so suppose a figure is located in quadrant 1. So which of the following sequences will result in an image that it's located in quadrant 2? So rotate 90 degree counterclockwise, then shift 1 unit up. And the figure is located in quadrant 1, and then you want to end up the figure in quadrant 3. So you want to rotate it 180 degree counterclockwise, then shift 1 unit down. And then 16C. And the figure is quadrant 1, you want to move that to quadrant 4. So you want to rotate 270 degree counterclockwise, and then shift 1 unit down. So again, from quadrant 1 to quadrant 2, it's about the rotation of 90 degree. Well, it's about the rotation of 180. And then from quadrant 1 to quadrant 3, it's about the rotation of 270. And now the next one, so which of the step will cause the rectangle to map onto itself? So according to the selection, it's about reflect across the x-axis and then shift 8 units up. So once you reflect it across the x-axis, so this one turns out to be -2, and then -2 plus 8, then that'll be 6. And same thing happened right here. So 2 reflected across the x-axis, so it turns out to be -2. And then you want to move 8 units up, so -2 plus 8, then that'll be 6. So it's about the reflections and then the translation. And that's selection D there. And which of the steps will cause the rectangle to map onto itself? So here's another way to do it. So reflect across the x-axis and then shift 9 units up. Reflect it over, so you got -3 plus 9, then you get, well, then that turns out to be -3, so -3 plus 9, then you end up with 6, which is up here. So this one's supposed to be 2, 4, 6, and then 8. It's hard to read that. And here's another one. So you want to find another one that makes sense. So reflect across the y-axis and then shift 9 units to the right. And then you end up with the exact same image. So 18a. So which of the following best describe the reflectional symmetry? So the reflectional symmetry that shows the quality of design has, if it maintains all its characteristic when it's reflected over the axis lying in its plane. So this one is just a description of the reflectional symmetry. And then the next one, similar, reflectional symmetry. Okay, so 19a. So this one is all about the line of symmetries. So which of the following best describe the axis over the design is reflected? So the line of symmetry. So what is the line of symmetry about? So the line that divides the design into two congruent parts. So let's say that you're sitting right in front of a mirror. So the mirror would be the line of symmetry. And which of the following best describe the line that divides the designs? A design so that every point on one side of the line coincide with a point on the other side of the line of symmetry. So here's what we got. It's a hexagon. It's a regular hexagon. The reason why it's regular because all sides are congruent. So how many line of symmetry are the regular hexagon are in the regular hexagon below? So we got 6 of those. So 6 bases. So 6 line of symmetry. Here's 1, 2, 3, 4, and then 5, 6. And how many line of symmetry are in the regular pentagon below? 5. Pentagon. So 5 size figure. Octagon, line of symmetry, 8 of them. If just set up the line of symmetry in the midpoint of one pair of aligned segments, you'll see that they're all considered a line of symmetry. Again, they're all allocated right at those midpoints of the line segments. And then the next one, which of the following polygon has 3 lines of symmetry? So 3 triangles, equilateral triangles, not just like a regular triangle, it's an equilateral triangle. It guarantees that all 3 sides are equal. And which of the following polygon has 9 lines of symmetry? 9. So that means regular nonagon. 5 line of symmetry, regular pentagon. So 22, which property allowed the design to maintain all its characteristic when it's rotated around a point in the plane? It's a rotation symmetry. Keyword for that, rotation. So what is that rotational symmetry about? So the quality of design has if it maintains all the characteristic when it rotates around a point in its plane. So that one is called a point of rotations symmetry. So we'll talk about that. And here's another one, rotational symmetry. And which of the following in the figure is the figure rotate about the rotational symmetry? So it's called a point of symmetry. So anytime that you try to rotate something, you need to follow through the point of symmetry. It's called a rotational point of symmetry. So that's just a description. So the definition of a point of symmetry. Point of symmetry again. And then 24a, which of the following figure has reflectional symmetry? So the one that's like this, like the symmetrical trapezoid. Figure B. And which of the following figure has a reflectional symmetry? Trapezoid again, A. Reflectional symmetry, so line of symmetry here, so then that would be this one right here. Choice D. 25. The interior angles of a regular hexagon below measure 120 degrees, so each angle is 120 degrees. And the hexagon has rotational symmetry. And which of the following is the measure of an interior angle after a 90-degree rotation around the point of symmetry? So when does one rotate? The measure of the angle still remains the same. So that means it's still considered 120 degrees. So this one is same thing. So interior angle is 108. So once you rotate around 90 degrees, so the measure of the interior angle still consider the same, 90 degrees. Well, it's still the same, which is 108 degrees. So again, this one is just considered an angle rotation, but the other one, it's just the measure of the interior angles. So again, rotational symmetry, so guarantee that the shape, the angles, everything remains the same. And here's another one. So regular octagon, so the measure of the interior angle is 135. So after that 90-degree rotation around the point of symmetry, so the measure of the interior angle still remains as 135 degrees. And then 26, so which figure repeat the tessellation? Tessellation is showing that the pattern. So we got yellow, black, black. So this one will be figure D, or black, yellow, black, yellow. And which figure repeats in the tessellation shown below? So things that we use for the floor tile. So here's the one. So the one that with the symmetrical line, showing that translation. Figure B. The rest of this, they're also showing some kind of transformation, but this one's a rotation. This one is kind of like a dilation. This one is like a rotation with dilation. But the one that guarantee it's the same shape without changing any kind of pattern, then that would be selection B. So here's another tessellation. So we do have a white, black triangles upside down, white, black triangles. So here's the one. So selection D. And which of the following best describe an arrangement of repeating shapes that have no space or overlaps between the shapes? So then that'd be tessellation. As you can see that there's no space right in between. And it shows like a pattern. So that shows that an arrangement with the repeating shapes. So now the next one, which of the following best describe tessellation? Again, an arrangement of repeating shapes with no space or overlapping between those items. 27, C. Okay, so shape cannot have space between them. 28. Which of the following best describe a semi-regular tessellation? It used more than one type of regular polygon. The rest of the selections, they're not that kind of precise. So the first one is saying that it used only one type, but actually used more than one type. And C is saying that just use irregular polygon. They cannot be considered irregular polygon, because that will be looking kind of ugly. And then it used circles and polygon. Not necessarily to be circle, can be any kind of polygon. It can be triangle, square, pentagon, hexagon, heptagon, nonagon, octagon, any kind of polygon. But as long as they're regular. And then which tessellation used more than one type of regular polygon? So that one would be the semi-regular tessellation. And 28C is quite similar. So now 29. So 29, which of the following is the characteristic of a regular tessellation? It used only one type of regular polygon.